So let's get started. So I'm Guilherme. This is Tom. We are both production network engineers at Facebook. Our job title is responsible for making sure that the data center devices are actually passing bits as they should. This doesn't happen all the time, but well, that's why we're here. And here on this presentation, here in this talk, we're going to talk about why introducing Minipack for us in the operations side of the house is important, what are the sort of wins that we got, and Tom is going to explain a little bit how we did this and make sure that we had this manageable platform in our networks. This is a brief agenda, so we're going to run about 20 minutes or so. Going to reserve a couple of minutes in the end for us to ask us questions if you want to, or if you want to, we can chat later during the downstairs in the booth. One of the major trends that we are seeing in our data centers is the increase of change. So due to the OCP hardware, white box switching, whatever else you want to call it, we are seeing the increase of the number of platforms that we're introducing is increasing in a faster pace. So before we had a switch that should have lasted 10 years in the fleet because it cost $500,000. Nowadays, with the price that we're paying for OCP hardware and the speeds and feeds that we need on our systems, we have the need to actually put in place faster, more power efficient platforms in a increased change of pay, faster in the fleet. So for us to set up the stage and understand what we are talking about here, I'm going to give a brief introduction about the Facebook data center networking. Going from bottom up, we have the RSWs, which is, some might call them the TORs, so they sit on the top of our racks. So all of our servers connect to the stores. All of our servers are single home, so there's no mumbo jumbo between VPCs or dual homing switches. Makes the design a little bit simpler. Uplinking the RSWs, have the FSW layer. So with the FSW layer is aggregating the traffic between many RSWs. We can have up to 48 RSWs per pod. And grouping FSWs and RSWs in a pool of devices, we call them a pod, right? Which again, can have up to 48 devices. Inside the same building, and aggregating the traffic between the multiple pods that we have inside the same building, we have the SSW layer. Some of you might know this as a super spine, where the FSW is the spine layer, right? But we just use a different nomenclature here, right? And in our region, our data centers, they sit inside a region, and the region is as a grouping of buildings. And so that we can enable the traffic between different buildings in the region, we have the FA layer. The FA layer aggregates the traffic between the different buildings in the region. So if data center 1 wants to talk to data center 2 in the same region, which is roughly up to 10 kilometers apart, they'll hit the FA layer. And the FA layer is also responsible for aggregating the traffic that goes out to the backbone, right? Because the backbone is a constrained resource, so we have a limited number of uplinks, a number of fiber routes, and that's the role of the FA layer, aggregating the traffic between buildings and also out of the backbone, right? So gonna use the RSW, FSW, SSW nomenclature across this talk. What is the status? What is the scenario that we had before introducing Minipack, right? We have mostly Wedge 100s, which is a Tomahawk-based platform, as our top-of-rack switch. This is continued to this day, but we still have a long tail of devices that were deployed before a long time ago. Long time in Facebook terms is 3-4 years, right? Where we got Wedge 40s, which is a previous generation, or even vendor devices. On the upper layer, on the FSW layer, we have a mix. We've been deploying Backpack for the last few years, but we still have a long tail of devices, of vendor devices, still deploying this layer. On the SSW layer, which is the layer above, the super spines, we have mostly vendor gear, and on the FA layer we have a mix. Some regions are still running on FAV2, which is the design based on vendor gear, but we are transitioning to the FAV3 layer, which is based on FBOSS, disaggregating both the platform and the hardware out of the switch. If you might want to have a look about this, we did a talk at last year's OCP Summit about the introduction of FAV3, and on this year about H-Grid, which is the FAV4, the next generation of the aggregation layer. Some of you might remember the backpack, which was our previous aggregation switch. So for you that don't remember it, it consists of 8 line cards, right? Each line card is a completely separated and disaggregated control and measurement plane. So, and as is the fabric cards. The fabric cards, their purpose is to switch the traffic between the different line cards, right? So if we have traffic going from port 1 to port 2 on the same line card, of course it doesn't need to hit the fabric card. But if it goes from line card 1 to line card 2, it hits one of the fabric cards to switch the traffic between the platforms. It is a nice platform, some interesting ideas, but in the end, what it does is aggregate all those 12 different control planes and measurement planes and data planes in a single chassis and providing up to 128 100 gig ports to the user, right? At that point in time, it was what we have available. Those are the ASICs available and so on. So the solution to provide this is using those 12 chips. So we have a 8U solution consuming X amount of power and so on. And what Minipack is giving us is the same capacity with a single management plane, with a single control plane. So of course we have power, cooling, space savings, and also on the operational side, it's way easier to handle a single switch than handling 12, right? And that's what I'm trying to say here, is that we learned some lessons out of the backpack, right? Is that, yes, technically it was fine to use the 12 different management planes, but that increased the complexity of our operations a lot, right? So from provisioning those chassis was way more complex than provisioning a single chassis solution. To draining, to RMAing a single line card, it was very painful process for the field guys, for automation guys like me, and even though our asset management system had to be changed to support this new model. So we learned our lessons and decided going forward, a solution like Minipack fits way better our use cases and tools. As you might remember, the Minipack, it has 2 flavors. It's a Arista and OCP approved hardware. They are more or less the same thing, right? Meaning they are both based on Tomahawk 3. They can expose up to 128 100G ports, but they have a small difference between the number of fans, the sensor they have on board, and so on. But they're basically the same. Well, what matters in the end is that they are providing 12.8 Ts of capacity to us. And that's actually one of the challenges for us on the operational side of the house, because we have to support these different platforms, different OSs running on the same platform, which is something that is pretty interesting, right? Because we have different combos of platform, OS, and rows. So we can have an SSW based on the Arista platform running FBOSS or running EOS, depending on the data center, depending on the application. And the same thing with Actom, with the Minipack, where we can have it running FBOSS, where previously we have it running Backpack. And another classical problem that we have is that we are working on brownfield deployment. It's not like we are, hey, let's rip and replace all of our switching fleet and replace this for Minipack. This will be great, but it's not financiable, responsible, or possible, right? And those are some of the problems, some of the challenges that we had while introducing Minipack to the fleet. On the beginning of this project, of the operationalization project, we have to define some clear requirements, right? Some of those requirements is, what do we need to monitor? These are the sensors that we want to monitor. This is the fans, the temperature that we have for the die on this ASIC or that ASIC, and also what tools we need to change, right? Because we have a plethora of in-house tools, and we need to make them support and have feature parity with the current platforms. Because it wouldn't be great for our few guys or for whoever else to be introducing a new platform with less capabilities or less support than we have for the current platforms that we have in production. So ensuring feature parity and defining MVP is pretty important during the operationalization part of the Minipack. And now I'm going to pass the word to Tom, which is going to talk about how we put this thing in production.
Cool. So thank you, Guilherme. My name's Tom. I'm also a network production engineer at Facebook. From Guilherme, you just heard about like the current state of the Facebook's network infrastructure, predominantly in the data center. He also talked about the evolution from Backpack to Minipack, which is a huge win in and of itself. But what I'm going to do is I'm going to talk a little bit about what we call new platform introduction. And this is really just a program that we name for when we introduce this device into the fleet, right? So there's some things that we do to make sure that we're comfortable. I'll talk about that a little bit more in a minute. But what have we done? Well, we've basically improved MPI. How have we done it? We've done it with more automated testing. And specifically, the testing that we've focused on, so there's a lot of things we need to do, tooling, automation, different things. I'm going to focus, because we have a small amount of time, on what we call the remediation pipeline, and that's really like the workhorse and a key part of how we're able to operate this network with a small number of people and such a large scale of devices. So why? Guilherme spoke about this. You know, the rate of change is increasing, CapEx is decreasing, so these things are happening more and more. So we learnt lessons from Backpack, and we've applied those to Minipack, and that's what we want to share today. So I'm going to give you some context now for just what I'm about to speak about. There's 3 things I want you to take away from this. It looks simple, but this blob in the middle, network infrastructure, that's our footprint. That's where all these devices are. That's what we consider our product, right? Our product is reliable and performant network capacity. At the end of the day, if it's not performant and reliable, it's just boxes sitting there doing nothing. But because it's infrastructure, you know, we know that these things break, things go wrong. That's expected. And what we do is we have what we call a remediation pipeline, but what it is at a high level is we try to automatically detect problems. We then raise some sort of signal or alert that is then consumed by more automation and code to go and try and, you know, basically automatically mitigate the problem, but if possible, remediate it completely to bring the capacity back in line. So this is key. This is the workhorse. I like to think of this as like 1,000 network engineers in a room that I can't go into, and if this is unhealthy, we have huge problems. The third thing to draw your attention to here is what I've got as inputs. The thing is that this network infrastructure footprint is not static. It's constantly changing, and there's a whole bunch of things that can change that, and it'll be the same in other people's networks as well. But 3 of them that I think we can touch on quickly. Capacity. So think of just adding more devices. Think of going from 40 gig to 100 gig to soon 400 gig, things like that. The second one, design and topology. Good examples here would be this physical topology change, F4 to F16, logical topology changes, new routing protocols, anything that can change, you know, what goes on in our product, right? That network capacity that we're responsible for. And the third one, which is most relevant to what we're doing today, a new platform, right? We have Minipack, and you know, it doesn't seem that dissimilar as far as Guilherme showed. It's providing the same capacity, right? But it's a new chipset, new sensors, just a whole bunch of things. If things go wrong, like I said, if the remediation pipeline can't understand it, then we have huge problems. So, new platform introduction. This is the process that we use. There's a lot of testing involved, and you know, any of this testing that is manual, we want to automate. So what are we talking about here? Is it going to play nice in production? And what I mean by that is, can we work with it? Can other engineers work with it? But more so, can our automation understand it? Is it going to interoperate with other devices? Is our tooling going to understand it? All these things, but specifically today, and you know, the principles applied to other things, but you know, is the remediation pipeline going to understand it? We're production engineers, and we like to say that we care about how things fail, how they scale, and we use automation heavily for that. So what's the approach that we've taken here? The thing that I want to kind of stress is that this remediation pipeline that I'm talking about, that we're testing, it's a distributed system. And it's not necessarily the most complex thing in the world. Depends on what problem you're applying it to, but it's a distributed system. There's multiple components, and it's really key to either understand those components or, if possible, like unit test those components. The testing that I'm going to talk about in a second are examples of system tests or end-to-end tests, right? So start at the bottom of this pyramid when you're doing this kind of stuff. Understand what you're actually testing. The thing is that if you come up with a system test and it's successful and it works, it's a pretty high quality signal that like a whole bunch of what you're doing is healthy and working as it should. So testing process. This is really what we're doing. This is what a test looks like, and a test is effectively code. It is code. So what we do at a high level is we look at this remediation pipeline. What's it doing? Like I said, it's a workhorse, right? But it obviously had to know what to do. Well, we look at it and we reverse engineer something that it's doing. And then we create that problem and then make sure that the remediation pipeline will do its thing in a nutshell. But I'll quickly step you through it. So basically, we'll grab a healthy device. In this case, it would have been a Minipack, and that could be in like a lab Minipack. We could also do this in production as well by draining something first, trying it there, making sure it's good, undraining it. That's a whole nother kind of story. So we grab a healthy device, wherever that's from, trigger this failure condition, and we may have to emulate it somehow, and I'll talk about that. Then basically this is where the automation pipeline kind of starts. We wait for it to be detected, right? Once it's detected, I said, signal gets created, something consumes that, so the remediation starts, it finishes. At that point, we have some sort of result, like was it successful, was it not? We've also been able to collect a bunch of metrics on the way, which is useful. But once that happens, then we revert the failure condition. We ensure the device is healthy again. We log the result and any metrics we've collected to some centralized location for like analytical purposes. Then we release the device back into production, lab, the pool where it came from, so another test can run or another person can use it. High level, that's what a test is. Now, to make our lives a little easier, and to make things more efficient, what we do is, we have a bunch of tests, obviously. We feed these tests as well as a device, so as well as a Minipack, into an orchestration tool. The orchestration tool will then run those tests serially on the same device. And what it'll do is provide a summary of like, hey, you've made a change, so a change is made. We decide, okay, let's rerun our tests in an ad hoc fashion, and then we can see if there's been any regressions. And if there has been a regression, which test, which component, what failed. Maybe somebody in the Harbert team did a firmware update without telling us, who knows, but we can then figure out where it went down. So we also have the ability, using this framework, to do like continuous testing, so periodic, nightly, on change, and that has the ability to provide kind of earlier signal on if there's been a regression. You can talk to us after this, but some interesting things in doing these end-to-end system tests is that you find regressions in like third-party tools and things that you wouldn't expect to break, and so we've got some stories there. Cool, so I'm going to go through, we don't have a lot of time, but I'm going to go through two quick examples of what a test might be for us, right, when it comes to Minipack. So remember that, so the two examples of, or the use cases, I'm going to go with a software problem and a hardware problem, right? So these things are disaggregated chassis. That's usually how we separate it. We can run EOS, as Guilherme said, on a Minipack, or FBOSS on a Arista device. We test everything, but for this particular example, we're talking about an FBOSS device on a Minipack, and at the end of the day, these things are routers, right? They're layer 3 switches. We're using them to route IP. So they have a routing daemon. In this particular case, let's assume someone's done a bad push of an agent of the routing daemon, and now when it starts up, it crashes, and that's in some sort of loop. Now, we've seen this before. It's not uncommon. Obviously, it's not very common, but it happens, and if it does, we want to know about it. So the remediation pipeline knows about this. It's looking for this problem and this is a Linux system under the hood, so this routing daemon is a systemd service. We want to basically trigger this condition, so we can send effectively a sig kill to the process periodically to make it mirror what the remediation pipeline is looking at. Not even what the remediation pipeline is looking at or looking for, but what would actually happen in this case, right? And then at that point, we wait. As I said, we track it as it happens, but we watch the remediation pipeline. We let it do its thing. We collect metrics along the way. And at that point, a test is complete and we have some sort of result, and we can either go figure out why it didn't work or we move on to the next test. And you can see how this would apply to other software problems, right? You just basically, anything that can go wrong, we try and automatically fix it. And what we're doing here is testing that automation. So a slightly more interesting example would be a hardware failure. Ideally, to do this, we start this MPI program early, when there's still potentially hardware revisions and things could change, and it might just be a firmware update or something like that. But in this example, we have a fan that's not responsive in a chassis. So maybe the fan is died completely, maybe it's low RPM and it's under a threshold. Whatever the condition is, we want to know about it, and we expect the remediation pipeline is going to fix it for us. So ideally, you want to trigger this as close to the source as possible. With unlimited resources, you'd ask somebody in the DC to unplug a fan, you'd run your test, see if it's detected, put it back in. That doesn't scale unless you have robots. Well, I don't think we do. The condition, though, here, we can emulate this, and this is one of the benefits of open networking, I think, where the management plane is separate from the control plane. So if you're familiar with some of the OCP networking hardware, you basically have a separate controller, effectively, like running whether it's OpenBMC or something. And so that is responsible for a few things, but let's just call it system management. Basically polling sensors of environmentals and things like that. So what we can do is we can leverage that to basically funge the values it's reporting back and make it appear like a particular piece of hardware is either not there anymore, or it's, one of its sensors is completely off. Maybe something looks like it's about to become on fire because the voltage is whatever, right? In this case, though, it's a fan. So let's lower the RPM under a threshold, wait for the remediation pipeline to do its thing, right? Again, same sort of thing as what I said earlier. This is where there's a lot of wins as far as speed goes, because we constantly want to be testing this sort of stuff, and just having to rely on another human in another time zone perhaps to go and do something. So some of the challenges, really the single biggest challenge here is that we're testing a distributed system, and so it's critical to test the underlying components first, or at least understand what they are, right? Follow that pyramid. If you start at the bottom, your life's going to be easier. When we didn't, that's when we were getting not as high a quality signal, but by doing that lower stuff first, it's definitely in your best interest before doing these end-to-end system tests. As I said, we catch regressions. If there is a problem in one of these underlying components, your end-to-end test is not going to be successful. So to minimize false positives, it's in your best interest to do that. Understand what you're testing. What does the future look like? Well, what does the future look like? We're going to continue to improve this MPI thing that we're doing, right? Our ability to introduce new platforms into the fleet. Guilherme touched on it at the start, and it's pretty key. It's that this stuff's happening more and more frequently for us, and I imagine others in the industry as well. So Minipack's not the last. Requirements are constantly changing. People want more capacity. There's this thing called rich content. It's pretty crazy, the amount of change. So we're expecting more platforms, and the more efficient we can do this, the better. And the other thing that in the future for us, I think, is that we want to keep improving the continuous testing efforts we're doing, and this is going to allow us to catch these regressions even sooner, right? So think about, we run these things ad hoc, nightly, and maybe we detect something has changed and then we run them again to give us earlier warning, right? So in summary, this has been a pretty big win for us, particularly after coming from the backpack NPI. The result really is that we've sped up MPI, right? We've made it quicker, but we've also made it so we're more confident when we do it. When we put these in the fleet, which we have them in the fleet right now in production. So that's the result of this work that we've been doing. I guess, I want to say that you can do this too, and regardless of scale, I still think there's benefits here. And I'm talking about testing when you're introducing new platforms. You don't necessarily need a fancy framework or anything like that. You could look at something like Ansible as far as orchestration. Any of these sort of things are great. What's key is that tests are code. So code is documentation. Code can be reused and iterated on and improved. It's repeatable and consistent, and I think that's really key. So yeah, I mean, if you want to speed up your new platform introduction using automation, you can and you should reach out to us, because we've been doing this and we're kind of constantly improve it. That's all we have. Happy to discuss anything really related to this type of stuff. Minipack.
So testing, it's easy to see if your routing daemon has correct. What about some pathological or grave failures if your next hops are wrong, or something that is not necessarily physically down, but
Yep.
how do you model intended state and how do you validate against your operational state?
Yeah, so that's something we do outside of this, but I'll touch on it and I'll tie it back. So basically, we map or we model the desired state for the network, whatever it may be, right? Like, these are the devices, these are the interfaces, these are the line cards, this is who they should peer with, these are the addresses, as much as possible. And then if there's a discrepancy there, based on us looking and comparing, then we create some sort of alert. And that's relevant because that's a good example of something that the remediation pipeline could handle, right? If there's somehow an incorrect IP address has been applied to an interface when it shouldn't have been, that peer is probably going to go down, and that's a condition that we want to know about, but we don't want to actually go and look at every individual instance of that. The remediation pipeline would take care of it. So that's something that we would also test.
And we also generate a signal via white box and black box monitoring, right? Because we collect the data that the box is reporting, say, hey, my sessions are up, I have this whole routes installed in my feed, all good, great. But the box can lie to us, right? Box are nasty things. And then we do some black box monitoring. So we inject synthetic traffic, make sure that it's able to spray across all the interfaces and catch that if we are missing any of those flows in the network too.
Have you automated your ACAs? Do you understand why things happen and the order of them?
ACLs, did you say?
No, root cause analysis.
Right.
We have some of that automated. So we have automated root cause analysis for box going down. So
Yeah.
when we detect a box going down, we say, hey, this thing's supposed to be here, it's not anymore. There's a problem. So
Yeah.
we collect the logs, we understand what happened to the thing and say, hey, these are parity error on ASIC blah, and because we already categorized that, right?
Yeah.
But some of the causes that we have categorized are not categorized yet, and that get escalated to a human so that the human can root cause the thing and then insert back to the database saying, hey, this is a condition when A, B, C, and D happen. This is the condition where we got a software failure or component A, B, C, or D failure.
So there's post-mortem process.
Yes.
But that would be like if we've as Guilherme said, if we haven't seen that before, that's more likely going to happen then. Our job a lot of the times is figuring out, is automation doing the right thing, and if not, why? And then if there's something new that we haven't seen before, how can we make automation do that in the future? But again, this all happens. This all makes a lot of sense at scale. But I think just even introducing new platforms into smaller fleets, I think thinking about it in terms of writing code and using automation to do lots of tests is beneficial.
One more quick.
Yeah, please.
In band telemetry, have you started using it? Where are you?
For this?
Not yet. This is still in the works.
This particular silicon can actually use
Yes, but our software is not up to speed yet. All right. If anybody wants to talk to us, we'll be around here in the booth. Please reach out, and I think we need to give space for the next presenter. Thank you so much.